Good morning, everyone. In the last class, we have discussed that the crude oil, after refining, that is, after removal of saltish water, sulfur, and the soil particle, it is fed into a fractionating column where various components of petroleum or the crude oil they are separated depending their molecular weight and boiling point. So therefore, this is the setup which is used for fractional distillation. This is a fractionating column. Before passing into the fractionating column, because crude oil is in the liquid state, it has to be vaporized. For vaporization, through this pipe, the crude oil enters and gets vaporized and it is heated at 400 degrees centigrade. Now, since there is no oxygen, the combustion will not take place. Only the liquid state will be converted into vapor state. Now, these vapors having different molecular entities, it enters into the fractionating column, and depending upon their molecular weight and therefore the boiling point, they settle down at various stages of fractionating column or various heights of the fractionating column. So from the higher molecular weight components, they are converted immediately into liquid, and they are contains lubricating oil, the paraffin, waxes and asphalt. Then the, the vapor rises at 370 degrees centigrade fuel oil, then 300 diesel oil, isn't it? Both are almost mixed quantities are there. Then kerosene, gasoline and gases go from the top. The gases include the from C1 to C4 carbon atom. In between them, there is a petroleum ether. There is the naphtha is also here, isn't it? So only important fractions have been shown. It's not the complete fractionation. So we know that the majority of the compounds we need in the form of gasoline, kerosene and diesel oil, isn't it? The only limited use of lubricating oil and high molecular weight components are there. That is paraffin waxes in the form of the polymer industry, in the pharmaceutical and cosmetic industry and food industry. So, but only 10% of the total requirement of the total crude oil, we need only 10% in the form of this for the uh, uh, various industries. From the top of it, we are getting C1 to C4 carbon molecular weight components, which are there in the form of gases. So this also has a good amount, and therefore all cannot be utilized in the form of gas. So therefore, after fractionating, the kerosene oil will move to the respective column where it will be further certain things will be added. Similarly, diesel oil will also be will also go to another reactor where the certain purification will take place, such as desulfurization, denitrization, and deoxygenation. So these operations will be done both on the gasoline, kerosene, and diesel oil, isn't it? But the fractions which they carry of the hydrocarbon will remain the same. From the top of it, where we have good number of a good amount of gases are there, all cannot be utilized as such in the fuel, and therefore they will move into another column or reactor which is known as polymerization reactor. Very small molecular weight components will join together to form a larger component, gasoline, kerosene or diesel. Similarly, so from the gases, they will fed into a polymerization reactor in a refinery, and the heavy molecular weight components, they will be fed into a cracking reactor, where the larger molecular weight components can be cracked into a smaller one. So this is how this we have discussed already. And the reactor, the petroleum geology, you see cracking reactor is just the cracking of long chain hydrocarbon into a small chain hydrocarbon. For example, if you have normal decane, and if you crack it, it will be converted into normal pentane and normal and pentene. So if you add hydrogen further, then two molecules of normal pentane will be generated. And you know that normal decane is not a gasoline molecule, it's not a good gasoline molecule, and therefore it will be converted into a gasoline molecule, normal pentane and normal and pentene. So this is the cracking process. Cracking process is done in this way. This I have already uploaded. This is done in a catalytic chamber or a thermal chamber. We will discuss it later on. The first process is thermal cracking process, which was developed by Vladimir Shukhanov, a Russian scientist. And here he has used the thermally decomposition has taken place, and the reaction mechanism is homolytic fission, and therefore free radical formation will take place in case of thermal cracking process. Here you have free radical. This I have already uploaded, and you can read it. This is the mechanism for this. This already, you know, we are well aware of free radical mechanism. Just I am giving you for your convenience so that you can read it once again. This is the third slide on mechanism of thermal cracking. Then you have example we have taken for thermal cracking, that is butane. Just example because butane itself is a good fuel, and therefore there is no need to crack it. But still, just for example, we have given the butane. So butane is a good gasoline fuel. Then there are two types of then you have a catalytic cracking reaction. The thermal is the one which goes through the free radical formation. Here you have the catalytic reaction, cracking of butane. Two types of catalytic reactors are there: fluid bed catalytic reactor and gaseous phase catalytic reactor. So these are certain things which I have already uploaded, and you can go through this. This is the history of catalytic cracking reactor. Catalyst is used here is alumina or aminosilicates, isn't it? This is already zeolites, isn't it? Zeolitic material, silica or alumina is used for this. This is again same thing. This is a design of fluid catalytic reactor, fluid catalytic cracking unit. There's no need to remember it. A more simple diagram I will give you. The mechanism of catalytic cracking. This is based on the carbocation mechanism. This is the mechanism involved here, where catalyst is Lewis acid, which attacks on this, removes the proton and forms LH minus and a carbocation is generated, which then fractionated into the another carbocation and a molecule of simple lower molecular weight component is generated. Then this La combines with this one, forming forming a neutral molecule, and La is degenerated. This is the fixed bed catalytic cracking reactor, where you can see the heavy oil is introduced on heating at 425 degrees centigrade. Then it goes. Then you see the catalyst is kept at the various sides, isn't it? It is silica, alumina gel, or bauxite mixed with clay and zirconium oxide, or sometimes modified zeolites are being used. There are two catalytic chambers, both are maintained at 425 degrees centigrade. So, in the form of vapor, the oil enters into this because it is already heated to 425 degrees centigrade, and then enter into this catalytic chamber. The reaction takes place. The larger molecule components they are cut into a smaller one, and then these vapors comes out here, and they are fed into a fractionating column where various components are separated. So this is a fixed bed catalytic reactor where you have to use the fixed bed, where when it is the catalysts are exhausted, you have to remove it and refed it with the fresh catalyst, and you have to shut down the process. So this is a disadvantage, though it gives you a good amount of gasoline molecule. This is a moving bed catalytic reactor, where half of the catalyst is already there in the catalytic regeneration tank, isn't it, reactor, and half catalyst is used. And once the catalyst is exhausted, a fresh catalyst enters from a regeneration tank into the main reactor, and the main catalyst and the exhausted catalyst it fed back into the the catalytic regeneration tank, isn't it? Similar type of catalysts are obtained, and then reaction takes place. That is fractionation reaction. The cracking reaction takes place, and then cracked vapors go into the fractionating column, where they can be collected from the various sides of the collecting column. The advantage of this is that though the process is continuous and can be made automatic, and there is no need to shut down the process for regeneration of the catalyst. So this is certain major products which is obtained from either from the crude oil, which is obtained from mining, or by cracking, etc., isn't it? And this is the schematic flow diagram of a typical oil refinery. You don't have to remember these diagrams. Then comes the refining of gasoline. The gasoline is refined first, and then certain additives are added in order to improve the combustion characteristics or octane rating. You see, the refining process, that first thing is that you have to remove the sulfur. Sulfur is a very unwanted element in the fuel. Refining of gasoline is the removal of sulfur. Sulfur compounds are removed by Doctor's process, where the alkaline sodium plumbite is reacted with the oil, so that R organic sulfur RSH, isn't it? It gets converted into the lead lead sulfide, isn't it? And 2NOH, and then you have organic lead sulfide. You are getting here, and then this further sulfur is added, where lead is precipitated as lead sulfide is precipitated, and organic disulfide is generated. This is precipitated and this organic disulfide is removed by solvent extraction method. So then there are certain other methods for refining of sulfur, and this I have not completed yet. So you can go through the book. Hydrodesulfurization with the help of hydrogen of catalase, addition of hydrogen and catalase, the sulfur is removed. Similarly, nitrogen is also removed by addition of hydrogen and use of catalase. Oxygen is also removed in the similar fashion. Then the third operation is removal of coloring matter. Here, whatever coloring matter is there in the gasoline, mostly it is because of nitrogen. So you have already removed it. But still, if you want to do some coloring matter is there, then that can be removed by passing the oil or gasoline through the Fuller earth column, where all the coloring agent, coloring material will be absorbed. Then certain addition of inhibitor takes place. Certain inhibitors are added to slow down the oxidation reaction, thereby increasing the storage and transport properties of gasoline. Besides this, you have also add certain other additives which will improve the anti-knocking tendency of the fuel, is it, of the gasoline, and therefore certain other additives are also added. In earlier times, the knocking tendency or the of the engine was controlled by addition of tetraethyl lead, tetraethyl lead in addition to ethyl bromide. But now, since leaded petrol has been banned completely, therefore we cannot use tetraethyl lead as a scavenger, free radical scavenger, and therefore one has to modify the structure of gasoline molecule in order to have better combustion characteristics or better octane rating. This is we are doing with the help of the process which is known as reforming of gasoline. For reforming also two types of reactors are there: thermal reforming reactor and the catalytic reforming reactor. Whether it is the refining or whether it is the cracking or polymerization or it is reforming, the catalytic process is always preferred as compared to thermal process. Thermal refining run at this temperature. This I have already given you in your slide and uploaded it. Catalytic reforming is done with the help of similar type of catalyst. Four main reactions takes place in the reforming process. One is the dehydrogenation reaction, where the molecule which are cycloalkane molecule, they are converted into benzene type of or aromatic compounds with the removal of hydrogen gas, where the octane number of this molecule is very low. Upon conversion it into the aromatic compound, or here it is toluene, then it improves to much higher level, near about it goes to 100 octane number. Here it is very low. So because first reaction which takes place is the dehydrogenation reaction in the reforming process. The second reaction is the isomerization, where the straight chain molecule with the same molecular weight gets converted into a branch chain molecule, and therefore it gets converted into, where the heptane molecule gets converted into 2,5-dimethylhexane, is it, octane molecule. 1, 2, 3, 4, 5, 6, 7, 8. So octane molecule gets converted into 2,5-dimethylhexane. Here the octane rating is 0, and here it is much higher. It is around 80, 90 or something. So therefore, this is the isomerization is the second type of reaction that takes place in the refining process. Then you have dehydrocyclization, where hydrogen is removed from either side and it gets converted into the cyclic structure, and the molecule of hydrogen is liberated. So this one, normal leptane, 1, 2, 3, 4, 5, 6, 7. Normal leptane has octane number 0, and it has been given an octane number 0. Now this 0 octane molecule gets converted upon dehydrocyclization. So cyclization takes place plus the dehydrogenation takes place and gets converted into toluene, which has this structure, or toluene has the octane number which is very close to 100. From 0 to octane number, the molecule has changed to the 100 octane number, and additionally 4 hydrogen molecules have been generated, which can be utilized elsewhere as a byproduct. So this is the third reaction.
Sir?
Yes.
Sir, what is the difference between the first and the third, sir? Then
This is a straight chain molecule. You see, this is not cyclization. Second one, yeah.
Sir, first, sir.
First.
Yes, sir.
This one.
Yes, sir. First and third.
This was already cyclized. You see, this was a cyclic structure, isn't it? Which has been converted into aromatic structure. Here, in the third one, you can see it was a straight chain molecule, isn't it? In the first one, the octane number is not 0, isn't it? Octane number is not 0. It is much less, but it's not 0. And the nature of the structure is alicyclic compound, isn't it?
Yes, sir.
It is cycloalkane type of molecule. Here, in the third one, you can see it is normal straight chain molecule, isn't it? Which has been first of all cyclized, and then it is dehydrogenated to give you a toluene molecule. From 0 octane number, it gets converted into a molecule that is toluene, which is having very close to 100 octane number, isn't it? So that is the change. Then the fourth reaction is hydrocracking reaction, where a straight chain molecule, a long chain one, isn't it, normal leptane. Why we have taken normal leptane? Because normal leptane has 0 octane number, isn't it? Then with the addition of hydrogen, it gets converted into isopentane and ethane molecule, isn't it? Both of them have very good octane rating, isn't it? So this way, or simply it can be cracked into 2, isn't it? Simply it can be cracked into 2 and give you 2 molecules, straight chain molecule, but a small molecular weight. You know that they will discuss it later on, that how the octane number decreases with increase in the carbon chain length. This is mechanism, catalyst and mechanism. Alumina silicate is generally used. Heteropolyacids are also used. Certain heteropolyacids are also used as catalyst in case of this type of reaction. Then you have some other aspects of reforming process, history as well as the catalyst use. This is the semi-regenerative catalytic reforming unit. Regenerative means the catalyst is regenerated, isn't it? You don't have to remember this diagram. isn't it? Just it's for sake of completion, and those who want to see that how, what is the uh, um, schematic level of, or schematic diagram of a refinery. This is part of the refinery. Then coming over to the gasoline engine, what is knocking, isn't it? And what is octane number and how it is improved. This will be discussed here. In the engine operation, let us go first of all to our the download the attendance. I'm very sorry, because of my poor health, I could not explain that in much better way. So therefore, the engine operation, suppose you are taking a 4-stroke engine. What do you mean by 4-stroke engine? 4-stroke engine means one fuel cycle, isn't it, is completed in 4 strokes. You see, this is the engine head design. Here you have a cylinder, isn't it? Entire cylinder is here. Then it is a piston which is attached. Piston is attached with a connecting rod, and then to the crankshaft, etc. Isn't it? So the mechanism is that it goes up and then it comes down, goes up and it comes down, isn't it? Here you have a spark plug, you have 2 valves, and also here somewhere you have a fuel injector. In the modern earlier engine, it was carburetor. Now we are MPFI or micro fuel injectors are there, which will spray the fuel in the form of very small droplets or nanoparticles. Better is uh, the 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 smaller is the size of these nano droplets, better will be the activity. So here you can see this is how what happens, that you can see here this diagram. Here you see this is the entire cylinder, these two, and this is piston. Now you see what happens, that if you pull down this piston here, what it will do in the first stroke, I will show you later on. So you have to displace it to the maximum, isn't it? So suppose this is the maximum volume, empty volume, which can be obtained by this engine, isn't it? And this is the minimum volume when the piston is up, isn't it? When the piston is up. When the piston is up. So this is the maximum volume which can be obtained by pulling the piston down to the maximum. And this is the minimum volume here, which can be, which is known as minimum volume, which is when the piston goes up to the highest point, isn't it? Now, the this, suppose this volume is taken as V1, this volume is taken V2. So V1 upon V2 is known as compression ratio. V1 upon V2. You can see volume before compression 488 cc. After compression 60 cc. So you can have The ratio between 480 and 60 is 1:8. The compression ratio of this engine is 8:1. Now you can see the how the work is done by a piston, by engine. Work is done in a way that piston was here, it will pull down, isn't it? Then the maximum displacement which can be achieved, which will be, then this will be sent to the wheel somehow by connecting rod or etc. So maximum work can be obtained by maximum displacement of this piston in the cylinder. So that is why the efficiency of the engine and the work output is directly related to the CR, compression ratio. Maximum the piston will be pulled down, maximum work will be attained. So therefore, this is CR ratio. Now coming over to the earlier diagram, that is here you can see. This was V2, minimum volume which can be achieved. Now what happens? Here in this one, 4-stroke engine, it is wrongly given. This is should be, the arrow should be down, isn't it? The diagram is not correct. So you can make in your diagram. This is the diagram, but it is showing that it is started going up. So this is not, the first stroke is the suction stroke, not compression stroke. It is known as suction stroke, where originally the piston was here. Then it will move down and it will suck air from this wall. It will suck air from this wall. So that it will suck air from this wall. So air will be sucked in and the piston is moving down. It reached there. Then this is known as, you can correct in your diagram. This is the, I'm unable to do this right now. So this is the not compression stroke. This is a suction stroke. Now this suction stroke, then when it is finally averaged to the maximum volume, then it will start going up. Now it will go up and what will happen? It will reach the maximum level here. That is V2. V2 volume will be achieved, as I have told you earlier. So the air will be compressed. Air will be compressed, and therefore it is known as compression stroke. Air will be compressed. The air which you have sucked here will be compressed, and in this compressed air, the oil droplets or the fuel injector will inject the fuel, isn't it? So good amount of pressure is there, and therefore, and then a spark from the spark plug will be created, or it will be the fuel which will already in the droplet form, and a good pressure is there, so it will be in the form of vapor state. Now this fuel vapor, which is a mixture of oil and air, because air you have sucked it here. So it is a fuel air mixture which is in the form of vapor state. It will be ignited by this spark plug, spark from the spark plug. So the combustion reaction will take place. Now what will happen? The gaseous products will form. Gaseous products will form. Now these gaseous products which are formed, which will compel the piston to go down. This is known as power stroke. This is known as power stroke. So power stroke has created, and it will become down to the maximum level here, isn't it? Up to this level, isn't it? It is maximum level. Maximum displacement means maximum, a better CR ratio means maximum displacement and therefore maximum work done, maximum efficiency of the engine. So now this comes down. Then in the fourth stroke, which is known as not power stroke, it is known as exhaust stroke, isn't it? Exhaust stroke. Then again, though it is a power part of power, but in this one, when again it goes up, what will happen? That the suction valve will be closed and the exhaust valve will be open, and whatever combustion products are formed, they will go into the exhaust pipe, and again it will reach here. Then the first cycle, again the second cycle will start from this one. So this is how the engine works. What happens that compression ratio, I have told you, the compression ratio, and more with the compression ratio, better will be the work output and the efficiency of the engine. This I have already uploaded. You can theoretically more power can be produced from a higher compression ratio, and increase in the compression ratio result in a higher degree of compression. Combustion occurs at the faster rate because the molecules of the air fuel mixture are packed tighter, isn't it? So this is the, and the displacement is maximum. This is also, now what happens sometimes, that if you have a fuel which can be ignited at a lower temperature, isn't it? At comparatively lower temperature. For example, you have the normal heptane molecule, isn't it? In the gasoline class, if you have normal heptane molecule, what will happen? It is a state heat molecule. So when the normal heptane is there inside this, isn't it? What will happen? When the piston was going up, or compression stroke has taken place, isn't it? What will happen in the second cycle? The first cycle is completed, and then in the second cycle, when whatever is remaining unburned fuel is there, suppose, or in a fresh fuel, if normal heptane is more, for example, then what will happen? Due to the compression, that is the extra pressure, etc., the fuel will be ignited before the spark from the spark plug. So the piston which was going up, isn't it? Because fuel is there, so the pressure inside is very high. So certain molecules, not all molecules, certain molecules, they will be ignited even before the spark from the spark plug. And when they will ignited, what will happen? The piston which was going up will be pulled down, and at this point of time, a knocking sound is produced by the engine. You see, because engine was going up, the piston was going up, but because of the uncalled for, or the molecules which can be ignited before the ignition from this spark from the spark plug, the combustion reaction has started, and the piston which was going up has been pulled down with the impact, and the sound is cracking. The knocking sound is produced by the engine. So good amount of energy is converted into knocking energy. It will be utilized for knocking the engine, and therefore the displacement of the cylinder will be lessened, because the cylinder, the piston has not reached up to the maximum, and therefore the displacement will decrease, and therefore the fuel which has been utilized here will not have the maximum efficiency. By the same engine, if you don't have, suppose you have isooctane, which is a very good fuel, gasoline molecule. If you have a isooctane molecule, suppose you are having pure isooctane, what will happen? Depending upon the CR ratio, the piston will move to the maximum because isooctane has a very good anti-knocking property. What does it mean? That it will not be ignited very easily, isn't it? And therefore, unless spark from the spark plug, isooctane will not be ignited. So therefore, the piston will move to the maximum height here, and therefore the displacement will be large, and therefore the efficiency will be large. And this is known as highest usable compression ratio. Okay, you have some compression ratio, but because of certain molecule, for example, pure heptane, that compression ratio cannot be utilized fully. But if you have isooctane as a pure fuel, then it can be achieved. That is, your compression ratio can be achieved to the maximum, and therefore the efficiency will be maximum, because efficiency of the engine depends upon the maximum displacement which it can which can occur by this one. So there are the normal heptane has lowest usable compression ratio for a test engine. Of all the other things are non same, but only you are changing normal heptane, pure normal heptane. What will happen? The efficiency will decrease because this will be ignited, pre-ignited in the presence of high pressure even before the spark from the spark plug. So the piston which was going up has been moved down forcibly, making us knocking sound, isn't it? So lowest will be the utilization of compression ratio when you are using normal heptane as a pure fuel. And that is why its octane rating number has been given or assigned 0. What does it? It does not mean that if you have normal heptane, pure normal heptane, your motorcycle will not start. It will start, but the efficiency will be very poor, and therefore it has been given and assigned a number 0. It is an assigned number because it gives you in a test engine the lowest compression rate, usable compression ratio can be obtained by normal heptane. For isooctane, the highest usable compression ratio has been achieved, and therefore its octane number has been given 100. So now your your sample or generally the fuel lie between 0 and 100, isn't it? So depending upon how much your sample matches with the percentage of isooctane in the normal heptane and isooctane mixture, and that will decide that what is the octane number of your test fuel. So that is why the octane number has been assigned. Here then you have certain things about compression ratio, which I have already discussed. Preignition is same as what I have told you, the highest usable compression ratio. This I have already designed, isn't it? The aromatic fuel benzyl can be used at higher CR without knocking than a straight chain paraffin. This you can read from the notes. Knocking I have told you, knocking and octane rating. This I have already told you. Now the question is why certain fuel they have lower octane number and other fuel they have higher octane number. This slide I have already discussed that normal octane, isooctane has the highest usable compression ratio, and therefore it has been assigned a octane number 0. The normal heptane has the 0 octane number, because it gives you the minimum usable compression ratio of a test engine, and this is the octane number, volume of percentage of isooctane, the reference fuel given the same law. Well, the test fuel. Now there are two types of octane number. One is known as the road octane number, and another is the motor octane number. RON or road octane number is also known as the research octane number, is measured at an engine which is moving at 600 rpm, isn't it? And in take air temperature. Take air temperature, whatever temperature of air is there, that is taken, and 100 rpm. Then whatever compression ratio you or the efficiency you get, it is known as RON. Then MON is motor octane number, which is a sort of which operates at 900 rpm, and higher intake air temperature is taken in this case. So two types of octane numbers are there, RON and MON. Now MON, this I have already discussed. The another indicator which is used for this is known as anti-knocking index, AKI, anti-knocking index. This is the ROM plus MON divided by 2 is known as the anti-knocking index. Chemical structure and octane rating. I was discussing that why certain molecule will be ignited before the spark from the spark plug. The reason is that those molecules which can easily form the free radical at a lower temperature, they can generate free radical, and this free radical, due to the presence, because instability, it can be ignited very easily, and therefore if those molecules, the knocking tendency decreases with increase in the compactness of the molecule, double bond and cyclic structure. That knocking tendency decreases means anti-knocking tendency increases when the molecule is compact, it has a double bond and it has cyclic structure than a straight chain molecule. In case of normal paraffins, the anti-knocking properties decreases with increase in the chain length of the hydrocarbon chain. That's why you can see normal butane as 90, higher than normal pentane, which is 60, which is higher than normal hexane, which is 29, which is not higher than normal heptane, which is taken as 0, isn't it? So as the chain length increases in a straight chain paraffinic molecule, the octane number decreases. Then you have third one, more is the branch structure, better will be the octane rating. For example, you have 2-methyl-hexane. 2-methyl-hexane is a branch chain structure. Then 2-dimethyl-pentane, same molecule, isn't it? Methyl-hexane, 7, now 2 plus 5, 7, carbon atom. Only the branching has changed. Now you can see the octane number increases from 55 to 80. More is the aromatic hydrocarbon such as benzene and toluene have higher octane rating than alicyclic counterpart. This I have already told you. In case of olefinic molecule, more is the olefinic nature, or when the double bond moves from terminal 1 butene to 2 butene, terminal to center, the knocking tendency increases. anti-knocking tendency increases. In case of diesel fuel, more is the straight chain structure, better will be the diesel fuel. And therefore, diesel fuel is knocking is also there and is measured in terms of cetane rating, not octane, but cetane rating. This you can go through your notes and you will find it. Then gaseous fuel, this is some properties of gaseous fuel, LPG, natural gas, biogas have not covered, isn't it? So this is all about this syllabus. First of all, stop the recording.